start the recording. Okay, now before you even copy this down, I want to focus on the first sentence here. It says that the number of people in a community who are exposed to a particular advertisement is governed by the logistic equation. Okay, that's a type of differential equation. Let me just ask you, if we were to model the number of people in a community who are exposed to a particular advertisement, and we said dn dt is equal to k times n, would that be an appropriate model for this situation? Why not, Matthew? What does this differential equation, dn dt equals k times n, model? Well, do you remember what the solution is? What the solution, if we say that what we're saying here in this differential equation here is that the rate of growth is proportional to the number of people who have seen the advertisement. Okay, and so, well, and also, would the number of people who've seen the advertisement, I mean, you know, so basically the rate of growth as the number of people see the ad, I mean, if we were to use this differential equation here, okay, and we're not going to for this scenario, but if we were to use it as the number of people increase who've seen the advertisement, then the rate that people see the advertisement increases also. And is that how it would be in a community?
No,
Like forever?
it would actually go, yeah, it would go the other way, because once people have seen it one time, you know, you've seen the advertising, you seeing it again probably has, well, it's just exposed to a particular advertising. So once you've seen it once, you've seen it.
And is are the people in the community on unlimited number?
No.
No. So what's eventually going to happen to the people in the community? Will eventually they all have seen the advertisement?
Yes.
They would. That's right, Tom. That's right. So we can't use this is an exponential growth model here. We
It has
can't
to be
use that for this
logarithmic, right?
situation. Right. So we need another model. All right. So that means, I'm sorry?
Logarithmic, right? Because it's eventually going to like slowly
Logarithmic.
plateau.
That's right.
Asymptotically. Okay.
That's right, Matthew. A logistic equation is equivalent to the logarithmic model that you learned in Calculus 2. All right, let me give you a moment to copy this down, this example. And incidentally, the logarithmic model in Calculus 2 was it was an optional section. It's called actually the logistic equation, but there are different names for it. But it was optional in Calculus 2. But now you're going to see it. So, all right. Okay, so in this problem, the number of people in the community who are exposed to a particular advertisement is governed by the logistic equation. And I'll show you what that is on when we get to the solution here. Initially, we're going to suppose that 500 people have seen the advertisement in the community. And then after, let me see here, 1 hour, let's say that's 1 hour, 1,000 people have seen the advertisement. What we want to do is solve for the number of people who've seen in the community who have seen the advertisement if it's predicted that the limiting number of people in the community who will see the advertisement is 50,000. Okay, so maybe the 50,000 is for, maybe these are for people who like, watch a particular program. Maybe this advertisement's, how many notice that certain programs have, like different programs have different kinds of advertising? How many maybe notice that on television? Well, I think I've noticed it, but yeah, Thomas says all the time, right? Okay, yeah, and that's right, and Christopher agrees. So, okay, may I go to the next page? And we'll look at the solution here. Andre, they could, yeah, well, sure. I didn't think about the internet, and this example is a little, it's kind of it's just a little example, but sometimes you see brand new things on the television in an ad, something you've never heard of. Sometimes, all right, so very good, very good. Well, all right, so let's go ahead here. What is this logistic model? This is the logistic model. The rate of growth, okay, in this case, the NDT, which is the growth rate for the number of people who've seen the advertisement, it is going to equal N times A minus B over N. Okay, and incidentally, A is greater than 0, and hold the phone. Let me just hold on that. One moment, class. Yeah, A is greater than 0, and B is greater than 0. So the idea here is you're saying that the growth rate is proportional. I want to be careful because we don't have a K in front, but I mean, but it's okay. I mean, you're saying that the growth rate is dependent on really two factors. One is the number of people who see the advertisement at time t, okay, and then another factor, which is essentially based on the number of people who have already seen the advertisement. In other words, the number of people who see the advertisement, it'll grow, but it's not going to. Eventually, the growth it'll slow down the growth because once I mean, it's sort of like a rumor, It's like a rumor. How many have noticed like rumors in the beginning kind of spread like wildfire, but then after time they die down? Matthew knows what I'm talking about. After time, you get a few people that haven't heard the rumor, still some people, but All right, Thomas knows what I'm talking about. And it's very important, yeah, very important here to talk about carrying capacity. The carrying capacity, right, Matthew? Yeah, good. That's right. That's right. The carrying capacity for the number of people who have seen the advertisement is equal to B over A. And I'm asking you, carrying capacity, what's special about this value B over A? If you look at the differential equation above and you consider when N equals B over A, what's interesting? Okay. In other words, what I'm saying is, hold on one moment, and I see there's some interesting chat things there, but let me just, if,
A should be greater than B, right?
well, I hadn't even thought of, well, B would have to be greater than A because the number of people have to be positive. I mean, like more than one. But if N equals B divided by A, okay. And this is the reason I like the recording. See, I don't have this on my paper here, but it's a good discussion question. If N equals B over A, when that happens, if the number of people who've seen the ad is equal to this value of B divided by A, okay, then what can you tell me about dn dt? What does dn dt equal? So substitute B over A for N here, where the N goes. That's right, Ann. Good. The growth rate equals 0. If the growth rate, when N, the number of people who've seen the ad, is equal to B over A, if you substitute B over A, well, this second factor here, this second factor would be 0 when N equals B over A. Or I should say, hold on, do I mean A over B? I think I have a typo here. It should be A over B. My mistake, class. Hold on. Let me fix that. My mistake. Hold on. I fix it on my notes also. Let me do that right now. Okay, so, and then Matthew was right. A would be greater than B. But hold on here. Let me just. Okay, one moment, class. Okay, so if the number of people who've seen the ad equals A over B, if you substitute A over B for N in this second factor, if you substitute A over B for N in that factor will be 0, and that means dn dt equals 0. So what happens when the population reaches the value A divided by B? What happens to the population? Does it grow anymore? Does the number of people who've seen the ad grow anymore?
No, I believe
No, because the change is 0.
That's right.
Change in
Good
time
comment.
is zero.
When the NDT, when the rate of growth equals 0, that means there's no more growing. If the growth rate's 0, that means no more new people are seeing the advertisement. In other words, everybody in the community has seen the advertisement, and you've reached carrying capacity. That's why when n equals a over b, you've reached and I'm sorry, this should be a over b also. Hold on, that should be a over b. Right? Yeah, that means carrying capacity. Are there any questions on that? Who's comfortable with that? Very important. Is everybody comfortable? Okay, Matthew's good. All right, wonderful. And okay, well then let's continue on here. Let's continue on. So in the textbook, they show how if you have this logistic differential equation, if you separate the variables, this is a separable differential equation, and as one student commented, it's an autonomous differential equation, and it is separable. If you separate the variables and then substitute in the initial condition that at time 0 you have n sub 0 people who've seen the ad, already seen the ad, then the general solution is this. And you may utilize this solution for section 3.2, okay? You may utilize this solution. You don't have to do separation of variables to get this solution unless I ask you to, like, you know, in the homework or on the exam. All right, but I think it's worth looking at the textbook at how they do it. All right, so now here's the thing. Here's the thing. This here is the form of the solution that the textbook gives, but the WebAssign likes a different form for the answer. So, like in WebAssign, if you were to type in an answer like this, WebAssign would not accept that answer. It wants this form of the answer. Okay, it wants this form of the answer. So what you need to do is this right-hand side here, you divide by b times n sub 0. You divide numerator and denominator by b times n sub 0. So you see I'm dividing the numerator by b times n sub 0, but then the denominator also, I'm dividing by b times n sub 0. And when you do that, you get that n of t is equal to a over b divided by that expression below. It's a more beautiful form for the to express n of t or p of t, you know, whatever your population is. It's a more beautiful form because you have a 1 here in the bottom left-hand corner. And I suppose WebAssign, the programmers, you know, they like it when you can get it in that form because, you know, you always got the 1 there in the bottom left corner. So that's fine. And actually, I've seen it much more in this form than in this form. All right. Well, now what we have to do, we have to try to come up with the answer. How many unknowns? How many unknowns are there? Hold on here. Well, we have one equation. We have one formula. So the unknowns, so A is unknown, right? B is unknown. But do we know n sub 0? Do we know n sub 0? Do we know initially the number of people who've seen the ad? That's right, Hulong, 500 people. So there are only two variables. Only two. Okay. And to solve for two variables, how many pieces of information do we need? That's right, Zachary, two pieces of information. That's right, Matthew and Thomas. Well, we have two pieces of information. We have two pieces of information in the problem. One is it's predicted that the limiting number of people in the community who will see the ad, the limiting number is 50,000. So what is 50,000? What's that stand for in the problem? That's right, Ann. Excellent. A over B. It's your carrying capacity. It's your carrying capacity. And also, we know that after 1 hour, 1,000 people have seen the ad. Okay, so given that, those two pieces of information, we should be able to solve for, we ought to be able to find the formula for n of t. So doing that then, here's what we do. So again, here's the formula for n of t. And what I'm going to do is I'm going to let t go to infinity. I'm going to take the limit. I'm going to take the limit of this n of t. And I'm going to look at it as t goes to infinity. Okay. So as t goes to infinity, what's going to happen to e to the negative 8t power? What does that go to as t goes to infinity? What does that function approach? Good, everyone. Good. It approaches 0. So therefore, the limit of n of t as t to infinity is equal then to a over b over 1, which is a over b, which is 50,000. So we're allowed then, where the a over b is here in the numerator, we can put in 50,000. Okay. Oh, also here too. I'll put in 50,000. And I know n sub 0 is 500. Okay, so now we use the next piece of information. After 1 hour, 1,000 people have seen this ad. And that gets us down to here. Let me give you a moment to kind of look it over. We'll see if there are any questions. One moment. Okay, so now if we're good here, uh, the right-hand side is going to be 50,000 over 1 plus 99 times e to the negative a. And now it's just a matter of solving for a, because that's the only variable that that's the only piece that we need to figure out. And so, this is just simple math here, just simple math. And may I go to the next page? All right, very good, Andrea. Very good, Thomas. Are there any questions? Okay, well, so now, of course, incidentally, going back to the previous page, I'm going to subtract 1 from both sides. And so I'll get 49 equals 99 times e to the negative a. And I have to solve for a. And again, now for a, you want to make sure that you have enough digits in your answer. Okay, you want to make sure you have enough digits in your answer. And now I figure out that a is 0.7033. And so then the number of people, okay, the number of people who have in the community who are exposed to the ad, who have seen the ad at time t, is equal to this function. How many maybe have seen this kind of thing in pre-calculus? I taught pre-calculus. I know that that is in there. How many have seen this like at Montgomery College, maybe pre-calculus or like things like this?
We did a good amount of this in Calc 2.
You had this in Calc 2. All right, Justin. Very good. Very good. Yeah, it's good stuff. It's good stuff. The logistic model is really a much more realistic model to describe population growth than the exponential growth model. I mean, exponential growth model is okay up to a point, but at some point, for normal populations, there's a restriction on resources. There's a carrying capacity, and so eventually, the population has to level off. It can't just keep growing and growing and growing. So the logistic model is a very good model. All right. I'd like to try to get one more example in here. All right, one more example. How many remember the fish problem, the harvest problem with the fish from last time? Okay, okay, and we like, all right, so, well, we can model fish population using logistic model. And so let me go to the next example if we're good here. Okay. Okay, Matthew, very good, very good. Let me give you a moment to copy this example down, and then we'll talk about it. Okay, all right, everybody. So we're back here. So let's look at this problem. Thank you. All right, so if a constant number of H fish are harvested from a fishery per unit time, okay, then a model for the population of fishery at time t with a harvest is given by this differential equation, where initially you have some p sub 0 population. So what they're doing is they're saying, all right, the population of fish follows logistic growth. Well, that makes sense because, you know, the fishery doesn't have unlimited amount of space, right? So that makes absolute sense that there would be a carrying capacity for the fish at the fishery. Now, why is there a minus here before the harvest rate H? Why is there a minus instead of a plus?
And that's because H signifies the number of fish that been harvested, so it's being taken away from.
That's right, Michael, and that's right, Zachary. You're harvesting fish means you're removing fish at that rate, so it's a minus. It makes perfect sense, you know. So okay, now in this case, they're giving you some values of A and B, and they're telling you the harvest rate. Under what conditions will the population become extinct in finite time? Okay, so we need to manipulate this differential equation here in order to answer this question. It makes sense. We have to put in the values of A, B, and H and study the differential equation. Okay, so I'd like to do that on the next page. Does everybody have the example copied down all right? Okay, very good, very good, very good. Well, then, all right, so look what I do here. I substitute in, hold on here, you know, my value of A was 7. My value of B was 1. And my H value was 49/4, the harvest rate. And what I'm going to do is usually we like things factored out, but what I'm going to do is I'm going to just distribute the P through the parentheses. And so I'll get dP equals 7P minus P squared minus 49/4. And then I'm going to factor out a negative from each term here. And if I do that, I'm going to get a dP dt equals negative of that quantity.
Should it be one negative and one positive, or both negative?
Well, you have negative.
The first term shouldn't it be? Wait. Okay, no, my bad, Professor.
Oh, no problem, no problem. Okay, well, so now it turns out that this can be factored as P minus 7/2 quantity squared. So I can write dP dt in this much more useful form here on the right-hand side. So I just rewrote the differential equation this way, but it's definitely a nicer way to write the differential equation. Okay, because now we can analyze it. We can analyze it, and what I do here, if I go down to the picture here, okay, on the left, what is this called here? Do you remember the name for this picture? Where we have, you know, it shows what the population P does.
Is it
Or
the
phase
phase?
portrait?
phase line. Good, a
Oh,
phase
phase
line.
line. Oh yeah.
Good, good. But you know, Christopher, you have the right idea. No problem. Hey, what's 7/2 called? What's that dot called on the phase line? There's a dot there.
Equilibrium.
That's right, Thomas. It's an equilibrium point. That's right. So when P equals 7/2, dP dt equals 0. The growth rate 0. So you know, because we have this minus in front of this P minus 7/2 squared, P minus 7/2, that quantity squared is always positive, but because we have a minus in front, that means solutions will be decreasing if your initial population is greater than 7/2, and if your initial population is less than 7/2. And 7/2, you could say, okay, maybe 7/2 thousand, okay, which would be 3,500, you know. And what I've done on the right here is based on the phase portrait, as you learned in section 2.1, based on the phase portrait, you're able to graph typical solutions to this differential equation. We haven't solved the differential equation explicitly. We could, wouldn't be hard, but we can qualitatively look at solutions. So of course, if your initial population is above 7/2, population would decrease till it reaches 7/2. Okay, and let me just see here one moment. Yeah, and if the initial population is below 7/2, the population decreases. Okay, but there's an interesting thing here. Let me give you a moment to. Let me just give you a moment here, a minute or two, one moment. Okay, so now, of course, when P equals 7/2, okay, when P equals 7/2, dP dt equals 0. And so, you know, that's why 7/2 is an equilibrium value. But here's something that's interesting. I want to say this right. When P is equal to 0, okay, that means when the population's extinct, the derivative is negative 49/4. Just substitute P equals 0 in for the differential equation. And so what this means is if you if you the slope, okay. You know, when we think of tangent lines, you know, of slopes, the tangent line right here, when the population equals 0, has a negative slope, the tangent line to the solution curve. And that means that the population has to be extinct at some finite time, capital T here. And in your homework, you're going to have to find that finite time, capital T. Okay, you're going to have to find that, and there's actually a help video on that. But to answer the question then, the population would definitely go extinct if your initial population were less than 7/2. Okay, so at the fishery, if the population, initial population, you know, let's say you buy this fishery. Well, if you buy the fishery, you better know if there's enough fish in there for you to harvest some fish. And if the initial population is less than 7/2, you know, that you're gonna end up having no fish, right? And this has to do also, you know, species going extinct. You know, if you have a, you know, like hunting, you know, like hunting, there are limitations on hunting, right? That's because you don't want the animals to go extinct. And well, I'll tell you, Matthew, I'd rather have 3.5 thousand fish than less than 3.5 thousand fish. But you get the general idea, and I know we're a little over time here. Are there any questions?
Yes, Professor.
Yes.
So when you
well, one moment, Matthew. I was just saying that, I mean, they didn't give any units for the problem, so I just like 7/2. I pretended like 7/2 meant like 7/2 of 1,000, so 3,500. That's all I was doing there. Yeah, a question, Thomas?
Well, it has to do with that. That 7.5 means 7.5 of what?
Well,
Because
7/2.
you might have
I mean,
started
you know,
with, I don't know, 100 or 500, but
no. Well, this
is
isn't.
it
This
saying
doesn't
that
relate
if you
to that
reach
problem.
7/2 of 500, then you will be depleted? Population
It
will be
depends what
depleted?
your
Is
units
that what it
are.
is, and it will not increase anymore?
Hold on, one moment. Let me stop the recording here.